Right now, as you settle in and get ready to sleep, something strange is happening inside your phone. GPS satellites above your head are solving differential equations to pinpoint exactly where on the surface of the Earth you are lying. The audio compression algorithm in your earbuds is decomposing the soundtrack into an infinite sum of sine waves, a method invented 200 years ago by a French mathematician studying how heat spreads through a metal rod. And somewhere in a data center, a neural network is learning to generate text, applying the chain rule of differentiation, a formula Gottfried Leibniz wrote down in 1676, with no idea that 3.5 centuries later it would run inside machines capable of holding a conversation in human language. All of this is calculus. 3 concepts: limit, derivative, integral. And from them flows all of modern science, all of engineering, all of physics, and a substantial part of economics, biology, and computer science. Calculus is so deeply embedded in the infrastructure of modern civilization that removing it would be like removing electricity. Everything would simply stop. When a meteorologist predicts a hurricane's path, the model is a system of differential equations solving themselves forward through time. When a cardiologist reads your heartbeat on a monitor, the jagged line on the screen has been cleaned up by a Fourier transform, another gift of calculus. When your streaming service compresses a movie into a file small enough to send over a wireless signal, it is using the discrete cosine transform, a direct descendant of work done in the 1700s by Leonhard Euler. When an engineer designs a bridge, the curve of the cables and the thickness of the beams are optimized using derivatives, the same mathematical tool that Newton invented during a plague. When a doctor adjusts the dosage of a medication, the rate at which the drug is absorbed and cleared follows an exponential decay equation, the simplest differential equation in calculus. When a SpaceX rocket lands itself on a floating platform in the ocean, the onboard computer is solving differential equations in real time, adjusting thrust hundreds of times per second based on continuously changing velocity and position data. You could go your entire life without noticing any of this. Calculus is invisible in the same way that gravity is invisible. Always there, always working, shaping the world second by second, but so fundamental that we forget it exists. The phone in your hand, the plane that brought you home last week, the electricity flowing through the wires in the wall. None of it works without calculus. None of it was even conceivable without calculus. When you hear the word calculus, you might picture a fat textbook crammed with formulas, or recall a miserable exam. But behind those formulas lies one of the most beautiful ideas in the history of human thought. An idea people in vastly different corners of the world arrived at again and again, because it is the natural answer to a question you cannot help but ask. How do you describe something that never stops changing? That answer has a history, long, tangled, sometimes tragic, stretching across 4,000 years and dozens of civilizations. And here is what is truly astonishing. Civilizations separated by thousands of miles and hundreds of years kept arriving at the same ideas, over and over, independently. As if the mathematics were not invented, but discovered, uncovered, like fossils buried in the ground, waiting for someone to brush away the dirt. Egyptians 2,000 years before the Common Era produced a formula whose rigorous proof requires integral calculus. Babylonians calculated Jupiter's trajectory by adding trapezoid areas under a velocity graph, essentially performing integration.
Archimedes inscribed infinitely many triangles inside a parabola, approaching the exact answer through infinite approximation. And in 14th century Kerala, India, a mathematician named Madhava and his students developed infinite series for sine, cosine, and arctangent, 250 years before the same thing was done in Europe. As if the ideas were hanging in the air, waiting for someone to reach out. Then, in the 17th century, Newton and Leibniz gathered all these scattered threads into a single system and ignited one of the ugliest intellectual wars in the history of science. A war that split European mathematics into two camps, set British science back by a century, and ended with one of the two geniuses buried almost without ceremony. Tonight we tell this story in full, from clay tablets to gradient descent in neural networks. Along the way, we will figure out what calculus actually is, not as a set of formulas for an exam, but as a way of thinking. We will understand what a limit means, why the derivative answers the question, how fast? Why the integral answers the question, how much in total? And why the discovery that these two questions are opposite sides of the same coin may be the most stunning intellectual breakthrough of the last 4 centuries. A few questions to guide us. How did ancient civilizations stumble onto these ideas thousands of years early? What exactly did Newton and Leibniz do that their predecessors did not? Why did the fiercest war in mathematics erupt between two people who arrived at the same result independently? And why does the same mathematical gesture Archimedes used 2,300 years ago work today inside every neural network on the planet? The whole idea of calculus boils down to two questions. How fast is this changing, the derivative? How much has accumulated, the integral? A driver glancing at the speedometer is looking at a derivative, the instantaneous rate at which position is changing. An accountant closing the books for the quarter is computing an integral, the total revenue accumulated over time. A weather forecast, a stock chart, a heartbeat on a hospital monitor, each one is a story about something changing, and calculus is the language for telling that story with precision. And the astonishing discovery at the heart of the subject is that these two questions, how fast and how much, are secretly the same question, asked in opposite directions. Answering one automatically answers the other. That link, the fundamental theorem of calculus, is what turns scattered techniques into a universal system. Think of it as layers, each era a new layer, a different civilization, a different mind, but the same dream. To understand a world that never stands still. Tonight we descend through those layers one by one, starting at the deepest and oldest, and slowly rising back to the surface. The descent will take us through ancient Egypt, Mesopotamia, Greece, China, India, the Islamic world, Renaissance Europe, and finally into the modern age. By the time we surface, you will understand what calculus is, where it came from, and why it matters. And with any luck, you will be fast asleep. Get comfortable. Close your eyes if you like. We begin at the very bottom. Around 1800 years before the Common Era, roughly 4,000 years ago, someone in Egypt wrote a series of mathematical problems on papyrus. We call it the Moscow Mathematical Papyrus, after the Pushkin Museum in Moscow, where it ended up, carried there by a circuitous path through collectors and antiquities dealers. The scroll contains about 25 mathematical problems, written in hieratic, the cursive form of Egyptian hieroglyphics, and among them is one that seems almost impossibly sophisticated for the era. It asks you to calculate the volume of a frustum, the shape you get when you slice the top off a pyramid. Imagine a pyramid built from stone, and then imagine cutting through it horizontally partway up, removing the peak and leaving a flat-topped solid. The papyrus gives concrete numbers, specific side lengths, a specific height, and then lays out a method for computing the volume. The method works. Think about the shape for a moment. A frustum
is wider at the bottom and narrower at the top, and the sides slope inward as you rise. Every horizontal cross-section is a square, but the squares get smaller as you climb. To find the volume exactly, you would need to account for the way that cross-sectional area changes continuously from base to top. And accounting for a continuously changing quantity is precisely what integral calculus does. Yet the Egyptian scribe, without any notion of calculus, wrote down a method that yields, in modern notation, the formula V equals h over 3 times the quantity a squared plus a times b plus b squared, where a and b are the sides of the two square bases and h is the height. And this formula is not an approximation. It is perfectly exact, mathematically flawless. The thing is, to rigorously prove that this formula is correct, you need integral calculus. You need to imagine slicing the frustum into infinitely many, infinitely thin horizontal layers, computing the area of each layer, which changes as you rise from base to top, and summing all those areas. That procedure, slicing, computing, summing, is a definite integral, a concept that would not be given a formal definition for another 3,500 years. How did the Egyptians arrive at it? We do not know. They had no algebra in the sense we understand it, no letters standing for unknown quantities, no equations to manipulate, no symbols for generalized amounts. They had no formal concept of proof, no logical framework for demonstrating why a formula must be true. Their mathematics, as far as we can tell from the surviving papyri, was entirely procedural. They stated step-by-step recipes for specific problems, working with concrete numbers, never with abstractions. Multiply 2 by 3, add to the result 4, divide by 2, that kind of thing. They were master calculators, not theorists. Perhaps they found the frustum formula empirically, by building physical models from clay or sand and carefully measuring volumes with water or grain. Perhaps a particularly gifted scribe noticed a pattern after working enough examples with different dimensions and guessed the general rule. Perhaps there was a line of reasoning, now lost, that approached the problem from a geometric direction we cannot reconstruct. All we see is the result, written in hieratic script on a brittle scroll, and the result is flawless. 4,000 years ago, in a civilization with none of the mathematical tools we consider necessary for serious reasoning about continuous change, someone arrived at an answer that requires integration. They did not realize they were doing anything beyond practical geometry. But the mind that found this answer was touching something very deep, a pattern that would echo forward through millennia. Now travel east, across the Sinai Peninsula, through the deserts, to Mesopotamia, the land between the Tigris and Euphrates rivers, in modern-day Iraq. Here, a different civilization was keeping its records, not on fragile papyrus, but on clay tablets, pressing wedge-shaped marks into soft clay with a reed stylus, and then baking or drying the tablets until they were hard as stone. These tablets have survived for thousands of years, far longer than papyrus, and archaeologists have recovered hundreds of thousands of them from sites across Iraq, many still bearing legible mathematical calculations. The Babylonians were obsessed with the night sky. They tracked the motions of planets, stars, and the moon with a precision that would not be matched for well over 1,000 years.
and they did it for the most practical of reasons. They believed celestial events foretold the future, and their kings demanded accurate predictions. Jupiter was a particular challenge. Unlike the Sun, which appears to move across the sky at a roughly steady pace, Jupiter's apparent speed changes. Sometimes it moves faster, sometimes slower, and sometimes it appears to stop entirely and reverse direction before resuming its forward motion. Babylonian astronomers wanted to predict where Jupiter would be in 60 days, and their method for doing so was remarkable. They drew something like a graph, time on one axis, Jupiter's apparent speed on the other, and broke the area underneath the resulting curve into trapezoids. Then they added the areas of those trapezoids. The total area represented the total distance Jupiter had traveled across the sky. That is integration. The area under a velocity curve gives total displacement. Any first-year calculus student today recognizes the idea immediately. And these Babylonian tablets date to roughly 350 years before the Common Era, long before anyone in Greece or anywhere else formalized such methods. What makes the Babylonian method so striking is its sophistication. These astronomers did not simply estimate, they used trapezoids, shapes with a sloped top edge, because they understood that Jupiter's speed was changing between their data points, and a trapezoid captures that change better than a simple rectangle would. A rectangle assumes constant speed over the interval. A trapezoid assumes speed is changing at a steady rate, rising or falling linearly. The Babylonians, in other words, were not just summing areas, they were choosing their shapes to track a changing rate, which is a conceptual step beyond mere addition. They did not call it integration, of course. They did not even think of it as a general technique. They had a specific astronomical problem, and they found a specific clever way to solve it. But what they were doing, breaking a changing quantity into small pieces and summing them, choosing the shape of each piece to follow the curve as faithfully as possible, is the beating heart of integral calculus. Yet neither the Egyptians nor the Babylonians took the next step. They solved individual problems with individual tricks, brilliant, precise, sometimes breathtaking tricks, but tricks nonetheless. They did not step back and say, there is something universal here, a single method that works for any shape, any curve, any process of change. They never asked the abstract question. Their mathematical imagination was tied to specific problems. This frustum, this planet, this harvest. And perhaps that is natural. Abstraction, the willingness to leave concrete problems behind and ask what all those problems have in common, is itself an intellectual invention, one of the hardest leaps the human mind can make. The Egyptians and Babylonians were superb practical mathematicians. They could solve any specific problem their world demanded. But the leap to generality, the idea that one framework, one set of rules, could handle all problems of continuous change, regardless of context, requires a different kind of thinking, one that separates the structure from the specific, the pattern from the particular. That leap would come later, from different corners of the world. Picture the situation. By roughly 500 years before the Common Era, civilizations across the ancient world had accumulated an impressive collection of mathematical results, formulas for volumes, techniques for predicting planetary positions, methods for computing areas of fields. But these results were scattered, isolated, and local. No one had asked the unifying question. No one had seen the common thread running through the Egyptian frustum and the Babylonian trapezoids and the volumes of pyramids and the measurement of curved surfaces. The results sat like beads without a string. The first person who pushed furthest toward that unifying vision in the ancient world lived on the island of Sicily, in the Greek city-state of Syracuse, about 1500 years after the Moscow Papyrus was written. His name was Archimedes, and what he did with a parabola was so far ahead of his time that 2,000 years later, mathematicians would still cite his method as the first true step toward calculus. Archimedes was born around 287 before the Common Era, and by general consensus, he was the greatest mathematician of antiquity, possibly the greatest until Newton, nearly 2,000 years later. He likely studied in Alexandria at the Great Library, the intellectual center of the Hellenistic world, where scholars from across the Mediterranean gathered to study geometry, astronomy, and philosophy.
But Archimedes returned to Syracuse, the prosperous Greek colony on the coast of Sicily, and spent his working life there, inventing the Archimedean screw for raising water, designing war machines that famously held off the Roman fleet during a long siege, and, in the quiet of his study, producing mathematics whose depth still astonishes. His deepest work involved a deceptively simple question. Find the exact area of a shape bounded by a parabola. A parabola is the smooth, U-shaped curve you see when you graph y equals x squared, or the arc a ball traces when thrown at an angle into the air. It has curved edges, and computing area is easiest for shapes with straight edges, rectangles, triangles, parallelograms. You can measure lengths and multiply. But when the boundary is a curve, when the edge bends in a way no ruler can follow, how do you find the area enclosed? Archimedes had no algebra. He had no coordinate system, no equations, no formulas in our modern sense. He had pure geometry and his extraordinary mind. Here is what he did. He inscribed one large triangle inside the parabolic region, the biggest triangle that would fit, with one side along the base and the opposite vertex touching the curve at its highest point. This triangle covered most of the area, but not all of it. Gaps remained, thin slivers between the triangle's edges and the curve, so he filled each gap with a smaller triangle. Now the fit was closer, but new, tinier gaps appeared between those smaller triangles and the curve. He filled those too, with even smaller triangles. Each step added more triangles, each generation tinier than the last. With each step, the total covered area crept closer to the true area of the parabolic region, and Archimedes could prove that the uncovered area shrank by a factor of 4 at every step, a geometric series.
In the limit,
Infinitely many, infinitely small triangles. The total sum converged to the exact answer, 4/3 the area of the original inscribed triangle. Not approximately 4/3, exactly 4/3. This is the deepest move in all of calculus, chasing an exact value by getting closer and closer, never touching it directly, but knowing with certainty that the difference between your approximation and the truth can be made as small as you wish. Archimedes performed this same maneuver with circles, approaching the value of pi from both sides simultaneously. He inscribed a regular polygon inside a circle and circumscribed another polygon around it. The inner polygon's perimeter was less than the circumference. The outer polygon's perimeter was greater. Then he doubled the number of sides, from 6 to 12, 12 to 24, 24 to 48, 48 to 96.
With each doubling, the two polygons hugged the circle more tightly, and the two perimeters squeezed toward each other, trapping pi between ever narrower bounds. A hexagon gives a rough estimate, a polygon with 96 sides, which is where Archimedes stopped computing, probably because the arithmetic with fractions was becoming enormously tedious. Pins pi between 3 and 10/71, and 3 and 1/7, a range so tight it remained the best estimate in the Western world for centuries. All of calculus is built around this one idea. You can obtain an exact answer by considering an infinite process of approximation. You cannot measure a circumference with a straight ruler, but a polygon with 1,000,000 sides gets arbitrarily close. You cannot find instantaneous speed by looking at a single frozen moment, but average speed over shorter and shorter time intervals converges to a definite value.
You cannot literally add infinitely many positive numbers. But if those numbers shrink fast enough, their sum converges to a finite total. The exact value lives at the end of an infinite process, and the miracle is that you can reason about that process rigorously, pin down the answer, and prove it beyond doubt. But Archimedes worked within a philosophical tradition that viewed infinity with deep suspicion. Aristotle had drawn a sharp line. You could talk about a potential infinity, a process that could be continued indefinitely, but not an actual infinity, a completed infinite collection. Zeno of Elea had illustrated the dangers with his famous paradoxes. Consider Achilles and the tortoise. Achilles, the fastest runner in Greece, gives the tortoise a head start. By the time Achilles reaches the spot where the tortoise was, the tortoise has moved ahead a little. By the time he reaches that new spot, it has moved ahead again, and again, and again, infinitely many times. Each remaining gap is smaller than the last, but there are always more gaps to close. Zeno's conclusion: Achilles can never overtake the tortoise because he must complete infinitely many tasks, and you cannot complete infinitely many tasks in a finite amount of time. The conclusion is obviously absurd. Of course, Achilles catches the tortoise. But Zeno's logic is hard to refute without the right tools. The resolution, of course, is that infinitely many time intervals can sum to a finite total. 1 plus 1/2 plus 1/4 plus 1/8 adds up to exactly 2. But that resolution, the concept of a convergent series, would not be stated precisely for another 2,000 years. In Archimedes' time, infinity was dangerous territory. So Archimedes proved his results by a method called double reductio, proof by contradiction. He never claimed the infinite process finished. Instead, he showed that the area could not be less than 4/3. That leads to a contradiction. And could not be more, another contradiction. So it must be exactly 4/3. Each problem required a custom geometric argument carefully tailored. His method was art, not technology. Brilliant, unrepeatable, and not transferable. He could not hand someone a set of rules and say, "Follow these steps and you will find the area under any curve." Every new curve demanded a new flash of geometric insight. And here is the remarkable postscript. In 1906, a Danish scholar discovered a manuscript in a monastery in Constantinople, a medieval prayer book. Underneath the prayers, barely visible, was mathematical text in ancient Greek. Modern imaging technology, including X-ray fluorescence, eventually revealed the original writing. It was an Archimedes treatise called The Method of Mechanical Theorems, previously thought lost for over 2,000 years. In the 13th century, a monk had scraped the mathematical text off the parchment. Parchment was expensive and reusable, and written prayers over it, turning a mathematical masterpiece into a prayer book. But the original ink left traces that modern technology could recover. In this recovered text, Archimedes described how he actually found his results, not by the polished proofs he published, but by slicing figures into infinitely thin strips and weighing them on a conceptual balance, exactly the way Leibniz and Newton would work 2,000 years later. He treated the infinite as real,
manipulated it freely, and arrived at his answers with stunning efficiency. But he then hid this method, knowing it would fail the strict standards of Greek mathematical rigor, and replaced it with the laborious proofs by contradiction that satisfied his contemporaries. Archimedes died in 212 before the Common Era, killed by a Roman soldier when Syracuse finally fell after a long siege.
Legend, perhaps embellished but too perfect to resist, says he was drawing geometric figures in the sand when the soldier arrived and told him to come along. Archimedes, absorbed in his work, replied, "Do not disturb my circles." The soldier killed him. The Roman general Marcellus, who had specifically ordered that Archimedes be spared, was reportedly furious. With Archimedes, the thread of proto-calculus in the Mediterranean world snapped. Rome built one of the greatest empires in history, but its genius was practical: roads, aqueducts, concrete, law, not abstract mathematics. Roman engineers could build a bridge, but they could not, and did not care to, prove theorems about the area under a parabola. The ideas Archimedes had been developing, infinite subdivision, convergent approximation, the relationship between curves and their areas, went dormant in the West for well over 1,000 years. His books were copied by a few scribes, studied by a few scholars, and gradually forgotten by the broader culture. But the ideas did not vanish from the world. The same patterns kept surfacing in other civilizations, on other continents, as if obeying some law of intellectual gravity, pulling every sufficiently advanced culture toward the same mathematical truths. In the 3rd century of the Common Era, while Rome was sliding into political chaos and the memory of Archimedes was fading in the West, a mathematician named Liu Hui was working in China. Independently, with no contact with Greek mathematics, he arrived at the method of exhaustion. He inscribed polygons inside circles, just as Archimedes had done, and by using polygons with hundreds and eventually thousands of sides, he computed pi to 5 decimal places. Same idea, different civilization, different century. The logic was identical. Approximate a curved area with straight-edged shapes. Make the shapes finer. Watch the answer converge. Liu Hui did not stop at circles. He applied similar reasoning to find volumes of solids, slicing 3-dimensional shapes into stacks of thin cross-sections and summing the volumes of the slices. A century and a half later, another Chinese mathematician, Zhu Chongzi, pushed the computation of pi even further, reaching 7 decimal places, a record that would stand for nearly 1,000 years. These were not lucky guesses. They were systematic calculations built on the same intuition that had driven Archimedes. The more finely you divide, the closer you get to the truth. Meanwhile, in the Islamic world, something equally important was happening, though it was less about new discovery and more about preservation and extension. After the fall of Rome, much of Greek mathematical knowledge survived only in Arabic translation. Scholars in Baghdad, working at the House of Wisdom during the Islamic Golden Age, from the 8th through the 14th centuries, translated Archimedes, Euclid, and Apollonius into Arabic, studied them carefully, and pushed further. The word algorithm itself comes from the name of the Persian mathematician Al-Khwarizmi, and algebra comes from the title of his most famous book. The Islamic mathematicians developed algebra as a discipline, creating tools that would be essential for calculus centuries later. Al-Khwarizmi's algebra gave mathematicians a new power, the ability to manipulate unknown quantities symbolically, to set up equations and solve them in a systematic way. Without this tool, calculus could never have developed in the form Newton and Leibniz would eventually give it. The bridge from geometry to calculus runs through algebra, and that bridge was built in Baghdad. Among the Islamic scholars of this era, one stands out for our story. Ibn al-Haytham, known in Europe as Al-Hazan, worked in Cairo in the early 11th century. He was primarily a physicist and astronomer, famous for his groundbreaking work on optics. But in the course of his research, he developed methods for computing sums of powers, the sum of 1 squared plus 2 squared plus 3 squared up to n squared, and similar sums for cubes and fourth powers. These are precisely the calculations you need for polynomial integrals. If you want to find the area under the curve y equals x squared from 0 to some value, you end up computing exactly these sums. Ibn al-Haytham did not frame his work as integration. He was solving particular geometric problems. But his formulas are the raw material from which integral calculus would later be built. Through Arabic translations, and through the flow of knowledge along trade routes and through Moorish Spain, these ideas eventually filtered back into Europe, arriving just in time for the mathematical revolution of the 16th and 17th centuries. But the most astonishing development between Archimedes and Newton happened not in Europe and not in the Islamic world, but in Kerala, a lush, tropical sliver of coastline on the southwestern tip of India. Kerala was a prosperous trading hub, connected by sea routes to Arabia, China, and Southeast Asia, and its mathematical tradition had deep roots. Indian mathematicians had been working with zero, negative numbers, and decimal place value notation centuries before these concepts reached Europe. Starting around 1350, a lineage of mathematicians centered in the town of Sangamagrama produced results that, when Western scholars finally became aware of them in the 20th century, were almost impossible to believe. The founding figure was Madhava of Sangamagrama, active around 1350 to 1425. Madhava and his students, the Kerala school, developed infinite series for trigonometric functions. Madhava's series for pi over 4 reads 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and on forever. Add infinitely many such fractions, alternating sign, and the sum converges to pi divided by 4. This is the same formula that Europe would later call the Gregory-Leibniz series, named after James Gregory and Gottfried Leibniz, who independently derived it in the 1670s, more than 250 years after Madhava. But the Kerala school did not stop at pi. They developed series for the sine and cosine functions, infinite polynomials that, term by term, converge to the exact values of these trigonometric functions. The sine series. Sine of x equals x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and on and on. The cosine series. Cosine of x equals 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, and so on. These are what we now call Taylor series, among the most important and widely used tools of advanced calculus. A Taylor series lets you write virtually any well-behaved function as an infinite polynomial, an endless sum of powers of x, each multiplied by a coefficient. This is how every scientific calculator and every computer evaluates sines, cosines, and exponential functions, not by some mysterious built-in knowledge of curves, but by computing a few terms of a Taylor series, which gives the answer to any precision you need. Let us pause for a moment on what an infinite series really is, because this idea will keep coming back. An infinite series is a sum with infinitely many terms. Some infinite series converge. They add up to a definite, finite number. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, adds up to exactly 2. Each term is half the previous one, and the partial sums creep closer and closer to 2 without ever overshooting. Other series do not converge. The harmonic series, 1 plus 1/2 plus 1/3 plus 1/4
plus 1/5 grows without bound. Each term is smaller than the last, and yet the sum eventually exceeds any number you name. Whether a series converges or diverges depends on how fast the terms shrink, and learning to tell the difference is one of the central skills of calculus. The Kerala school understood convergence intuitively and developed clever acceleration techniques to make slowly converging series converge faster. The basic series for pi over 4, 1 minus 1/3 plus 1/5 minus 1/7, converges excruciatingly slowly. You need hundreds of terms to get even a few decimal places of accuracy. But the Kerala mathematicians found ways to transform the series, grouping and rearranging terms so that each partial sum gave a much better approximation. Using these refined versions of Madhava's series, they computed pi to 11 decimal places in the 15th century, an extraordinary achievement, unmatched anywhere in the world at that time. So why is Madhava not called the father of calculus? The question matters, and the answer is clarifying rather than diminishing. The Kerala school had brilliant individual results: infinite series for specific functions, techniques for speeding convergence, accurate numerical approximations that surpassed anything Europe would produce for another 2 centuries. These achievements are remarkable and deserve far more recognition than they have historically received. But the Kerala mathematicians did not connect these results into a unified system. They did not formulate the fundamental theorem of calculus, the discovery that differentiation and integration are inverse operations, that the problem of finding slopes and the problem of finding areas are secretly the same problem run in opposite directions. They did not develop a general concept of the derivative, a systematic rule for computing instantaneous rates of change for any function. They did not create a general algorithm applicable to arbitrary functions. What they had were beautiful, precise components, gears and springs and escapements of extraordinary craftsmanship. What Newton and Leibniz would do, 2.5 centuries later, was assemble those components, and many others from many other traditions, into a working machine. A machine with a crank you could turn to solve any problem involving continuous change.
And by the 17th century, in Europe, all the threads, Egyptian, Babylonian, Greek, Chinese, Islamic, Indian, were about to converge, though few of the people involved knew the full history of what they were building on. The Greek texts had survived through Arabic translations. The Indian series may or may not have reached Europe through trade and Jesuit missionaries. Historians debate whether there was transmission or independent rediscovery, and the evidence remains inconclusive. What is certain is that by 1600, European mathematicians had at their disposal a richer toolkit than any single civilization had ever possessed. Greek geometry, Islamic algebra, a mature number system including decimals and negative numbers, the printing press for rapid dissemination, and a culture of competition and publication that rewarded priority. The stage was set for 2 men to do something none of their predecessors had managed: to build a complete, general algorithmic system for analyzing continuous change. By the early 17th century, after the long intellectual winter of the medieval period, European mathematics was experiencing a renaissance of its own. Greek texts, preserved and extended by Islamic scholars, had been translated into Latin and were circulating widely. The printing press, invented in the mid-1400s, allowed mathematical ideas to spread faster than ever before. And European mathematics was being pulled toward calculus by 2 powerful forces that had nothing to do with pure curiosity. The first force was astronomy, the science of motion. Johannes Kepler, working in Prague from the meticulous observations of the Danish astronomer Tycho Brahe,
had shown that planets move in ellipses rather than perfect circles, overturning 2,000 years of astronomical dogma.
He also discovered that planets sweep out equal areas in equal times, meaning they speed up as they approach the Sun and slow down as they recede, and that there is a precise mathematical relationship between a planet's orbital period and its distance from the Sun. Kepler described these patterns with extraordinary precision, but he could not explain why they hold. Why ellipses? Why equal areas? What force drives the planets along these particular paths? Explaining planetary motion required tools for analyzing continuously changing velocity and acceleration, tools for describing how fast something is moving at every instant, and how that speed itself is changing, and those tools did not yet exist. The second force was engineering and navigation. European powers were building empires, and building empires required precise maps, reliable artillery trajectories, and efficient ship designs. All of these demanded new mathematics for curves, areas, and optimization.
In the 1630s, the French philosopher and mathematician René Descartes made a breakthrough that would serve as the essential bridge between geometry and algebra. He introduced the coordinate plane, the idea of labeling every point in flat space with two numbers, x and y, measured as distances along two perpendicular axes. Before Descartes, a parabola was a shape you drew and studied with compass and straightedge, a curve whose properties you described in words and geometric constructions. After Descartes, a parabola was the equation y equals x squared, a formula you could manipulate with the tools of algebra. Every geometric curve became an algebraic expression, and every algebraic expression could be graphed as a curve. A circle became x squared plus y squared equals r squared. An ellipse became an equation with two squared terms of different sizes. The hyperbola, the spiral, the folium, all became formulas. This merger of two formerly separate worlds, geometry, the study of shapes, and algebra, the study of equations, was the essential bridge without which modern calculus would have been impossible. You cannot take a derivative of a shape drawn on parchment, but you can take a derivative of a formula written in symbols. Descartes gave us the formulas. He translated geometry into a language that algebra could work with, and in doing so he made it possible for the next generation to develop systematic rules for slopes, areas, and rates of change. Around the same time, Pierre de Fermat, a French lawyer and amateur mathematician who is today more famous for his last theorem, was developing methods for finding maxima and minima of curves and for drawing tangent lines. His procedure amounted to differentiation, though he did not use that language. He would take a function, substitute x plus e for x, expand the expression, subtract the original, divide by e, and then set e to 0.
The result was the slope of the tangent, the derivative in everything but name. Fermat's method was essentially the same as the modern limit definition of the derivative, and it worked for any polynomial. What he lacked was the conceptual framework to recognize this as part of a larger system. He treated each problem as a separate exercise, not as an instance of a general theory. He also applied similar reasoning to find the point at which a function reaches its highest or lowest value, the first systematic optimization technique in European mathematics. At a peak or a valley, the tangent is horizontal. The slope is 0. Set the derivative to 0, solve for x, and you have found the maximum or minimum. Fermat used exactly this logic, though he did not use the word derivative. In Italy, Bonaventura Cavalieri was approaching the same territory from a different direction.
In the 1630s, he proposed thinking about area as though it were made up of infinitely many, infinitely thin strips, what he called indivisibles. To find the area of a shape, you would imagine it sliced into these strips, like a loaf of bread cut into infinitely thin slices, and then sum the slices. Cavalieri's principle states that if two shapes have the same width at every height, they have the same area. An idea that connects directly to the modern integral, where you compute area by summing the widths, or heights, of thin strips across the figure. The idea was powerful and intuitive, and it gave correct answers for areas and volumes that had resisted all previous methods. But it was philosophically controversial. If each strip has zero width, how can infinitely many of them add up to a finite area? And if each strip has some tiny but positive width, then you have not captured the exact area, just an approximation with a small error. Critics like the Jesuit mathematician Paul Gouldin attacked the method on precisely these grounds. You cannot build something from nothing, no matter how much nothing you have. These objections would haunt calculus for 2 centuries, but in the meantime, Cavalieri's method worked beautifully for practical calculations, and pragmatic mathematicians were happy to use it, while leaving the philosophical worries for another day. And then there was Isaac Barrow, Newton's teacher at Cambridge, a man of formidable intellect who would play a pivotal but ultimately supporting role in the story of calculus. Barrow was a gifted geometer and a respected theologian. He would later resign his mathematics chair to Newton and devote himself to divinity. In his lectures in the 1660s, he stated and proved something remarkable. The problem of finding the area under a curve and the problem of finding the slope of a tangent line are inverse operations. If you define a function a of x as the area under some curve f from a fixed starting point up to x, and then you compute the rate at which a changes, its derivative, you get back the original curve f. In other words, differentiation undoes integration. This is the fundamental theorem of calculus, the single most important result in the entire subject, and Barrow had it. But Barrow stated it in purely geometric language, as a relationship between areas and tangents in a specific diagram. He did not turn it into an algorithm. He did not say, "Here is a general procedure. To compute an integral, find an antiderivative and evaluate." He saw the connection, but he did not see how to use it as a computational tool. It was as if someone had discovered that a key fits a lock, but had not yet thought to turn it. Meanwhile, the Scottish mathematician James Gregory and the English mathematician John Wallis were pushing integration further, computing areas and volumes with increasingly clever algebraic tricks. Wallis, in particular, developed methods for computing integrals of power functions, the area under x to the n, using patterns he spotted in numerical tables. He computed the area under x squared, x cubed, x to the fourth, and so on, each time finding a formula until he could state a general rule. He also produced an infinite product formula for pi that connected the circle ratio to an endless chain of fractions. These results were impressive, but they were still isolated achievements, individual formulas for individual problems, not a general system. All the pieces were now on the table. Descartes had provided the coordinate system, the ability to turn curves into equations. Fermat had shown how to find slopes and maxima, proto-differentiation. Cavalieri had demonstrated how to find areas by summing thin strips, proto-integration. Wallis had computed specific integrals by pattern recognition. Barrow had seen that these two operations, finding slopes and finding areas, are inverses of each other. What remained was for someone to take all of these separate insights, forge them into a single unified system with consistent notation and general rules, and demonstrate that system's power by solving problems no one had been able to touch. Two men would do this, working independently,
arriving at the same place from different starting points, in one of the most extraordinary coincidences in intellectual history. One was a reclusive Englishman hiding from the plague in his mother's farmhouse. The other was a gregarious German polymath who had not yet begun studying serious mathematics. Their work would change the world. Their fight over credit would become the most bitter feud in the history of science. Isaac Newton was born on December 25, 1642, in the village of Woolsthorpe in Lincolnshire, England. He was premature and so small that, as his mother later told it, he could have fit inside a quart mug. His father had died 3 months before his birth. When Isaac was 3, his mother remarried and left him in the care of his grandmother. The abandonment marked him for life. He grew up solitary, suspicious, easily wounded, and ferociously private. Qualities that would shape the history of calculus in ways no one could have predicted. At Cambridge, Newton enrolled as a subsizar, a student who paid for his education partly by performing servant duties for wealthier classmates. But once he encountered mathematics, everything else fell away. He devoured Descartes' geometry, the algebraic work of John Wallis, and the lectures of Isaac Barrow. Within 2 years, he had surpassed every mathematician in England, though almost nobody knew it because he told almost nobody. In the summer of 1665, the Great Plague arrived in Cambridge. The university closed. Newton returned to Woolsthorpe, to his mother's farmhouse, and there, in isolation, over the next 18 months, he did something almost without parallel in human history. He invented calculus. He discovered the laws of motion. He developed the theory of universal gravitation. He conducted experiments with prisms that laid the foundations of optics. One person, 22 years old, during a plague, in the countryside with no library, no colleagues, no internet. These months, the annus mirabilis, the miraculous year, are sometimes called the most productive stretch in the history of science. Newton called his mathematical method fluxions. He imagined curves not as static shapes drawn on paper, but as trajectories traced by moving points. If a point moves through space and traces out a curve, the speed of that point at any given moment, the instantaneous rate of change of position, is what Newton called the fluxion. Today we call it the derivative. Let us slow down here, because this is where the real teaching begins. Let us understand what a derivative actually is, starting from the simplest possible example. Imagine you are in a car. Over the last hour, you have covered 60 miles. Your average speed is easy to compute. 60 miles divided by 1 hour equals 60 miles per hour. But average speed tells you nothing about any particular instant. Maybe you were stopped at a red light for 5 minutes and then drove 70 miles per hour the rest of the time. Average speed smooths everything out. What calculus wants is something more precise. Your speed at a specific instant, not over an hour, not over a minute, at a single point in time. How can you measure speed at a single point? Speed is distance divided by time, and at a single point, both the distance traveled and the time elapsed are 0. 0 divided by 0 is undefined, meaningless. So you cannot compute instantaneous speed directly, but you can sneak up on it. Measure your speed over 1 second. That gives a good approximation. Over 1/10 of a second, better. Over 1,000th, better still. As the time interval shrinks, the average speed over that interval approaches a definite value. The instantaneous speed is the value you approach but never quite reach, the limit. The formal definition: the derivative of a function f at a point x is the limit of the expression f of x plus h minus f of x, all divided by x as h approaches 0.
The numerator is how much f changed. The denominator is the width of the interval. The ratio is the average rate of change over that interval. The limit, as the interval shrinks to nothing, is the instantaneous rate of change. Let us compute a derivative.
Take the simplest interesting case. f of x equals x squared, the parabola. What is its derivative at any point x? Compute f of x plus h, that is, x plus h squared, which expands to x squared plus 2xh plus h squared. Subtract f of x, which is x squared. You get 2xh plus h squared. Divide by h, 2x plus h. Now let h approach 0. You get 2x. The derivative of x squared is 2x. Think about what this means. At x equals 1, the parabola is growing at rate 2. At x equals 3, it is growing at rate 6, 3 times faster. At x equals 0, the growth rate is 0. The parabola is momentarily flat at its lowest point, the bottom of the U. The derivative gives you a complete description of how fast the parabola is climbing or falling at every single point, and it does it through a single elegant formula, 2x. Newton went further. He found the power rule. The derivative of x to the n is n times x to the n minus 1. You bring the exponent down as a coefficient and reduce the exponent by 1. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. This rule works for any power, positive, negative, fractional, and it gives you a systematic, mechanical way to differentiate any polynomial instantly. No more custom geometric arguments. No more case-by-case brilliance. A rule, an algorithm. He discovered the product rule for differentiating the product of two functions, and the chain rule for differentiating nested functions. The chain rule is particularly important and worth understanding. Suppose y depends on u and u depends on x. Then y depends on x but indirectly through u. How fast does y change when x changes? The chain rule says dy over dx equals dy over du times du over dx. The rate at which y changes with respect to x is the product of two rates: how fast y responds to u and how fast u responds to x. If you have a chain of dependencies, y depends on u depends on v depends on x, you just keep multiplying. Dy over dx equals dy over du times du over dv times dv over dx. The chain threads the derivative through the entire sequence. It does not matter how many links the chain has, 2, 5, 100. Each link multiplies by the next, and the final product is the total rate of change from end to end. 350 years after Newton, this elegant rule would become the mathematical engine of backpropagation, the algorithm that trains every neural network on the planet. Newton also connected calculus to physics in a way that transformed both subjects permanently. His second law of motion, F equals ma, says that force equals mass times acceleration. And acceleration is the second derivative of position, the derivative of velocity, which is itself the derivative of position.
So Newton's law is a statement about derivatives. The force acting on an object determines the second derivative of its position. From this single equation, combined with his law of universal gravitation, the force of gravity between two objects is proportional to the product of their masses divided by the square of the distance between them. Newton derived all three of Kepler's laws of planetary motion. Elliptical orbits, explained. equal areas swept in equal times, explained. The precise mathematical relationship between a planet's orbital period and its distance from the Sun, explained. Phenomena that Kepler had described empirically by painstaking observation, Newton derived mathematically from first principles using calculus. The planets did not merely happen to follow these patterns. They had to, because the mathematics demanded it.
For the first time in history, mathematics did not merely describe the regularities in nature, but explained why those regularities exist, predicted new ones, and unified seemingly unrelated phenomena under a single framework. Gravity on Earth and gravity in space turned out to be the same force, governed by the same equation, producing the same mathematical consequences. An apple falling from a tree and the moon orbiting the Earth obey the same law, computable through the same calculus. But Newton did not publish. For reasons that biographers have debated for 3 centuries, pathological secrecy, fear of criticism, perfectionism, a desire for quiet that bordered on the obsessive, he kept his calculus locked in private notebooks and shared it only with a tiny circle of correspondence. He had been bruised badly by an earlier dispute with Robert Hooke over his work on optics, during which Hooke publicly attacked Newton's theory of light, and the experience seems to have convinced Newton that publishing was more trouble than it was worth. Better to know the truth privately than to fight for credit publicly. When he finally published his masterwork, the Principia Mathematica, in 1687, arguably the most important scientific book ever written, he deliberately hid the calculus behind old-fashioned geometric proofs, as if unwilling to reveal the powerful new tool he had actually used to derive the results. Readers of the Principia could see the conclusions but not the method. The actual treatise describing his method of fluxions would not appear in print until 1736, 9 years after Newton's death. This secrecy planted the seed for catastrophe. Because meanwhile, a completely different mind, sociable where Newton was withdrawn, philosophical where Newton was physical, eager to share where Newton hoarded, was arriving at exactly the same ideas by a completely different path. Gottfried Wilhelm Leibniz was born on July 1st, 1646, in Leipzig, Germany, 4 years after Newton. If Newton was a brooding solitary, Leibniz was his mirror image, gregarious, endlessly curious, involved in half a dozen fields at once, and eager to share ideas with anyone who would listen. He was a philosopher, a diplomat, a historian, a logician, a jurist, and an inventor. He built one of the first mechanical calculating machines, called the stepped reckoner, capable of addition, subtraction, multiplication, and division through an ingenious system of interlocking gears. The machine was imperfect. It jammed, it miscounted, but the ambition behind it was characteristic of Leibniz's mind. He believed that reasoning itself could be mechanized. The disputes could be settled not by argument, but by computation. "Let us calculate," he once wrote, imagining a future where disagreements would be resolved by turning a crank. Mathematics, for Leibniz, was one pursuit among many, a thread in a vast tapestry of knowledge. And he came to serious mathematical research later than Newton, only after meeting the Dutch physicist Christian Huygens in Paris in 1672. Huygens gave Leibniz a reading list. Leibniz devoured it with an intensity that rivaled Newton's Cambridge years, and he caught up astonishingly fast.
Within 3 years, working in Paris and then in Hanover, he had developed his own version of calculus, arriving at the same core ideas Newton had reached, but from an entirely different direction, with a different vocabulary, different intuitions, and crucially, different notation. Where Newton thought physically, curves as moving points, derivatives as instantaneous speeds, the whole system rooted in the metaphor of a body hurtling through space. Leibniz thought in terms of geometry and form, in terms of infinitely small differences between neighboring values. If you have a curve, and you take one tiny step along the x-axis by a minuscule amount, Leibniz called dx, the corresponding value of y shifts by a tiny amount dy. The ratio dy over dx, the infinitely small change in y divided by the infinitely small change in x, gives the steepness of the curve at that point. That ratio is the derivative. Different philosophical starting point, different mental imagery, different language, but the same mathematics, giving the same answers to the same questions. In 1675, in his notebooks, Leibniz wrote the integral sign for the first time, an elongated letter S, standing for summa, the Latin word for sum. Integration, in his view, was the summing of infinitely many, infinitely small quantities, and the tall S was a visual reminder of that idea. He introduced the notation dx, dy, and dy over dx, and he designed his symbols with extraordinary care. The chain rule, for instance, looks like ordinary fraction cancellation in Leibniz's notation. dy over dx equals dy over du times du over dx. The du's appear to cancel, top and bottom, as if you were simplifying an algebraic fraction. They do not actually cancel. The expression is a limit, not a fraction. But the notation is so suggestive, so easy to remember and manipulate, that it practically teaches itself.
The world still uses Leibniz's symbols today. Every integral sign in every textbook, every dy over dx in every physics equation is Leibniz's. Leibniz published his calculus in 1684 in a paper in the journal Acta Eruditorum. The paper was dense and difficult to read. Even the Bernoulli brothers, who would become its greatest champions, struggled with it at first. Johann Bernoulli later recalled spending days poring over the paper before the ideas finally clicked. But the crucial point is that the paper was public. It was out in the world, printed and distributed, available for anyone to study and build upon. And the Bernoullis did build upon it, mastering it, extending it, solving problems that had resisted all previous methods, and teaching it to their own students. Through their efforts, and through the culture of open intellectual exchange that Leibniz had always championed, his calculus spread rapidly across continental Europe. Textbooks appeared. University lectures adopted the new methods. An active network of correspondence connected mathematicians from Paris to St. Petersburg, and in those long, detailed letters, which served as the scientific journals of the era, problems were posed, solutions were shared, and the power of the new calculus was demonstrated again and again. For about 2 decades, there was no conflict. Newton knew of Leibniz's work. Leibniz had visited London and seen some of Newton's unpublished manuscripts. Each acknowledged the other, cautiously. But as the new century turned, the atmosphere changed. English mathematicians began claiming that Leibniz had stolen his ideas from Newton during that London visit. Continental mathematicians countered that Newton had suppressed his work for decades and had no right to claim priority over ideas he had refused to share. In 1712, Newton, now president of the Royal Society, the most prestigious scientific body in Britain, convened an official investigation into the matter. He selected the committee members himself. He influenced the report. He may have written portions of it. The committee's conclusion, published in a document called the Commercium Epistolicum, was unambiguous. Priority belongs to Newton. But the process was more prosecution than inquiry, and continental mathematicians rejected the verdict as biased. The war grew vicious. Anonymous pamphlets appeared, though many were not anonymous at all to those who knew the handwriting.
Each side accused the other of plagiarism and intellectual theft. Proxy authors fought on behalf of their champions, publishing attacks and counterattacks in journals across Europe. National pride mixed poisonously with intellectual debate. England versus the continent. Newton's dots versus Leibniz's Ds. British empiricism versus continental rationalism. The dispute drew in some of the finest mathematical minds of the era. Johann Bernoulli championed Leibniz. John Keill championed Newton. Personal insults flew alongside mathematical arguments. The tragedy is that both men had plenty of room for glory. Calculus was more than large enough for two inventors, but neither could tolerate sharing it. Leibniz spent his final years defending himself against charges of theft, his reputation on the continent intact, but his standing in England destroyed. He wrote long letters, marshalled evidence, appealed to fairness. None of it helped. Newton was president of the Royal Society, the most powerful scientific figure in England, and he wielded that power without mercy. Gottfried Wilhelm Leibniz died on November 14th, 1716, in Hanover. He had spent his last years increasingly isolated, working on a massive philosophical project that he never finished. His employer, the Elector of Hanover, who had by then become King George I of England, did not attend the funeral. Almost no one did. He was buried nearly without ceremony, a stark contrast to Newton, who would be given a state funeral in Westminster Abbey 11 years later. The priority dispute poisoned mathematical relations between England and the continent for generations. English mathematicians refused to read continental work. Continental mathematicians ignored English contributions. Each side developed calculus in isolation, duplicating effort and missing insights that the other had already found. It was an intellectual tragedy born of ego and nationalism, and its effects lasted long after both men were dead. Today, the consensus among historians of mathematics is clear. Newton and Leibniz arrived at calculus independently. Newton reached the core ideas first, probably around 1665 to 1666. Leibniz developed his version around 1673 to 1676. Their approaches were so deeply different, physically motivated versus geometrically motivated, dot notation versus differential notation, fluxions versus infinitesimal differences, that independent invention is far more plausible than theft. The same ideas had been surfacing across civilizations for thousands of years. It would have been astonishing if two brilliant minds working in the same century, aware of the same predecessors, had not converged on the same answer. The cruelest irony of all, Leibniz's notation won. It was more flexible, more intuitive, more naturally suited to the chain rule, substitution, and the manipulation of multivariable expressions. England, out of loyalty to Newton, clung to his dot notation for over a century and fell behind continental mathematics as a result.
Only in the early 1800s, when a group of Cambridge reformers, including Charles Babbage, who would later design the first mechanical computer, campaigned for the principles of pure deism against the dotage of the university, did British mathematics finally switch to Leibniz's symbols. Leibniz lost the war for recognition in his lifetime. He won the war for the future of mathematics. Every time you write dy over dx, every time you see an integral sign on a blackboard or a screen, you are using his language. The language of a man who died thinking his life's work had been dismissed, never knowing that 3 centuries of mathematicians would prove him right. Now it is time to look inside the machine these two men built, to understand what inverse operations actually means, to see why the fundamental theorem of calculus is so staggering, and to watch the machine work on a concrete example. We have learned what the derivative does. It answers the question, how fast is this changing at this very instant? Now we turn to the other half of calculus, integration, which answers a different question entirely. How much has accumulated in total? Start with something concrete.
Imagine you are driving a car at a perfectly steady 60 miles per hour for 2 hours. How far did you go? Easy. Speed times time equals 120 miles. And if you graph your speed against time, the graph is a flat horizontal line at 60. The distance you traveled, 120 miles, equals the area of the rectangle under that line. Base of 2, hours, times height of 60, miles per hour. Area under the speed graph equals distance. Simple enough when the speed is constant. But what if your speed is changing?
You start slowly, pull onto the highway, accelerate to 65, hit traffic, brake to a crawl, idle at a construction zone for 10 minutes, then accelerate again when the road clears. Your speed graph is no longer a flat line. It is a curve, rising and falling irregularly, with peaks during highway stretches and valleys during slowdowns. The total distance you traveled is still the area under that speed curve. That fundamental relationship has not changed. But now the area is bounded by a shape with no straight edges, a shape that follows every twist and turn of your changing speed. How do you compute the area of something so irregular? Here is the idea, and it is the same idea the Babylonians used for Jupiter, the same idea Archimedes used for parabolas, the same idea that has echoed through 4,000 years. Break the time into small pieces. During each small piece, your speed is roughly constant. It does not change much in 1/10 of a second. Multiply that roughly constant speed by the length of the timepiece, you get the approximate distance for that tiny interval. Now add up all the approximate distances. You get an approximation to the total distance. The approximation is rough because your speed was not truly constant during each little piece. But make the pieces smaller, 1/100th of a second instead of 1/10, and each approximation gets better, and the total sum gets closer to the true answer. Make the pieces 1,000th of a second, 1/1,000,000th. In the limit, infinitely many, infinitely thin slices of time, each carrying an infinitely precise snapshot of your speed, the sum converges to the exact total distance. This limiting sum is the definite integral. Visually, you are filling the area under the curve with tall, thin rectangles. Each rectangle has a width, the length of the time interval, and a height, the speed during that interval. The sum of all the rectangle areas is an approximation to the true area under the curve. If the rectangles are wide, the approximation is crude. The tops of the rectangles jut above or dip below the curve, leaving gaps and overlaps. But make the rectangles thinner and more numerous, and the fit improves. 100 rectangles give a decent estimate, 1,000 give a good one, 1,000,000 give an answer so close to the truth that the error is measured in billionths. In the limit, infinitely many, infinitely thin rectangles, each a perfect snapshot of the speed at that instant, the sum converges to the exact area. This limiting process is called a Riemann sum, after the 19th century mathematician Bernhard Riemann, who gave it a rigorous definition. But the underlying idea is ancient, as old as Archimedes, as old as the Babylonians. What Riemann did was state precisely the mathematical conditions under which the limit exists. And the answer is well defined, closing the logical gaps that had troubled mathematicians since Berkeley. Now comes the thunderbolt, the result that transforms calculus from an interesting idea into the most powerful computational tool in the history of mathematics. The fundamental theorem of calculus says, to compute the integral of a function f from a point A to a point B, the area under the curve of f between A and B, you do not need to sum infinitely many rectangles. Instead, find a function f whose derivative is f. Such a function f is called an antiderivative of f. Then the integral of f from A to B equals f of b minus f of a. That is the entire procedure. Find the antiderivative, plug in the two endpoints, subtract. Let us try it. What is the area under the curve y equals x squared from x equals 0 to x equals 3? First, we need a function whose derivative is x squared.
We know the power rule. The derivative of x to the n is n times x to the n minus 1. Working backward, the antiderivative of x squared is x cubed over 3, because the derivative of x cubed over 3 is 3 times x squared over 3, which is x squared. Now substitute the endpoints. 3 cubed over 3 minus 0 cubed over 3 equals 27 over 3 minus 0 equals 9. The area under the parabola from 0 to 3 is exactly 9. One arithmetic step, instead of summing infinitely many infinitely thin rectangles. Think about what just happened. Integration, finding area, accumulating totals, and differentiation, finding slopes, measuring instantaneous rates of change, are inverse operations. They undo each other. If you differentiate an integral, you get back the original function. If you integrate a derivative, you get back the original function, up to a constant. These two problems, how fast and how much in total, seem utterly unrelated. One is about a single instant. The other is about a long accumulation. One is local, the other is global. Two different questions, two different geometric pictures. And yet, the fundamental theorem says they are two sides of the same coin. Knowing how to answer one immediately gives you the power to answer the other. The fundamental theorem is the deep structural backbone of calculus. Everything else, every technique, every application, every extension, rests on it. Without it, derivatives and integrals would be two separate tools, useful in their own right but disconnected. With it, they form a unified system of extraordinary power. Anytime you can differentiate, you can integrate, because integration is just differentiation in reverse. Anytime you can measure rates of change, you can compute totals. And anytime you can compute totals, you can recover the rates that produced them. With the machine assembled, let us look at some of its moving parts. Some key functions and their derivatives, each carrying a meaning worth savoring. The derivative of e to the x is e to the x. The function equals its own derivative, the only function with this property, up to a multiplicative constant. What does that mean? Its rate of growth at every point equals its current value. The bigger it gets, the faster it grows. This is why the equation dy over dt equals ky, rate of change proportional to current value, has the solution y equals y naught times e to the kt. This single equation describes populations of bacteria doubling every few hours, radioactive atoms decaying at a rate proportional to how many remain, money earning compound interest, and drugs being cleared from the bloodstream. All exponential processes, all governed by the same derivative. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. Sine and cosine are waves, identical in shape but shifted by a quarter period. If you keep differentiating, you cycle back to the start after 4 steps. Sine becomes cosine, cosine becomes negative sine becomes negative cosine becomes sine again. This cyclical behavior connects deeply to Euler's formula, which unites exponentials with rotations in the complex plane. A physical illustration to tie it all together. Drop a ball from the top of a tall structure, say about 328 feet. Ignoring air resistance, its height above the ground at time t seconds is given by h of t equals 328 minus 16t squared, using the American system, where gravitational acceleration near the Earth's surface is about 32 feet per second squared, and the factor of 16 comes from 1/2 times 32. Differentiate once. Velocity equals -32 t-feet per second. The ball speeds up as it falls, its velocity growing in magnitude with each passing second.
Differentiate again. Acceleration equals -32 feet per second squared, a constant. Gravity pulls with a steady force regardless of how fast the ball is moving. Now reverse the process. Integrate acceleration and you recover velocity. Integrate velocity and you recover position. Three physical quantities, position, velocity, acceleration, live on three rungs of the same ladder, connected by differentiation going down and integration going up. Physics lives in derivatives. We observe integrals. The force of gravity is a statement about the second derivative of position. What we see, where the ball is at each moment, is the integral of that force. The fundamental theorem is the bridge between the hidden mechanism and the visible world. And after Newton and Leibniz, the bridge was open. Mathematicians rushed across it with a hunger that had been building for centuries. The 18th century was the era when calculus found its stride.
Newton and Leibniz had built the engine. Now a generation of brilliant mathematicians would drive it into every corner of science, solving problems that had resisted all previous methods, sometimes with breathtaking speed. The first family to seize the new tool was the Bernoullis. Jakob and Johann Bernoulli, brothers from Basel, Switzerland, were among the earliest mathematicians to study Leibniz's published work, and they mastered it with a competitive ferocity that bordered on the pathological. The brothers quarreled constantly, over priority, over credit, over whose solutions were more elegant. But their competition produced extraordinary results. Johann Bernoulli posed a challenge to the mathematical world in 1696. Along what curve does a ball roll from one point to a lower point in the shortest possible time, under the pull of gravity? Intuition suggests a straight line. After all, the shortest distance between 2 points is a straight line, so why not the shortest time? But a ball rolling down a straight ramp picks up speed gradually. It starts slow at the top, where the ramp is gentle, and only accelerates as it descends. A steeper initial drop gets the ball moving faster much sooner, and the time savings from that early burst of speed more than compensate for the slightly longer path. The optimal curve turns out to be a cycloid, the shape traced by a point on the rim of a wheel as the wheel rolls along a flat surface. Newton reportedly received the challenge and solved it in a single evening, recognizing it as a calculus problem in disguise. Johann Bernoulli, on seeing Newton's anonymous solution, allegedly said he recognized the author as the lion by its claw. The brachistochrone problem, as it came to be called, launched an entirely new branch of mathematics, the calculus of variations.
Ordinary calculus finds the number that maximizes or minimizes a function. The calculus of variations finds the entire function, the entire curve, the entire path that optimizes some quantity. It would later become essential in physics, giving rise to the principle of least action, which says that physical systems evolve along the path that minimizes, or makes stationary, a certain quantity called the action. Mechanics, optics, electromagnetism, quantum field theory, all can be derived from variational principles. The brachistochrone was the seed, but the towering figure of the 18th century, and one of the most extraordinary human beings who ever lived, was Leonhard Euler. Born in 1707 in Basel, Euler was the most prolific mathematician in history. Over a career spanning 6 decades, he produced roughly 800 papers and several landmark textbooks. To give you a sense of scale, the collected works of Euler fill over 70 volumes. He wrote on calculus, number theory, graph theory, mechanics, optics, astronomy, and music theory.
he introduced most of the notation we use today. F of x for a function, e for the base of the natural logarithm, approximately 2.718, I for the square root of -1, the imaginary unit, the Greek letter pi for the ratio of a circle's circumference to its diameter, and the capital Greek letter sigma for summation. When you write a mathematical formula using these symbols, you are writing in a language that Euler largely invented. Perhaps the most stunning single result Euler produced is his famous identity. E to the I pi plus 1 equals 0. 5 constants, E, I, pi, 1 and 0, from 5 different areas of mathematics: analysis, complex numbers, geometry, arithmetic, and the concept of nothingness, linked in an equation of just 7 symbols. Where does it come from?
It arises from taking the Taylor series for the exponential function. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on forever, and substituting a complex number for x. Specifically, substituting I times theta. When you do this and collect the real and imaginary parts, you discover that e to the I theta equals cosine of theta plus I times sine of theta. Set theta equal to pi. Cosine of pi is -1, sine of pi is 0, so e to the I pi equals -1, and e to the I pi plus 1 equals 0. The formula reveals that exponential growth and circular rotation are the same phenomenon, viewed from different angles in the complex plane. It is the deepest surprise in mathematics. The number that governs growth and the number that governs circles are intimately, inextricably related.
Speaking of Taylor series, though their special cases were known to Madhava in Kerala centuries before the Scottish mathematician Brooke Taylor, they became one of the most practically important tools of the age. The idea is seductive in its generality. Any sufficiently well-behaved function can be written as an infinite polynomial, an endless sum of increasing powers of x, each multiplied by a specific coefficient derived from the function's derivatives at a single point. For example, e to the x equals 1 plus x squared over 2 factorial plus x cubed over 6 plus x to the 4th over 24, and so on. Sine of x equals x minus x cubed over 6 plus x to the 5th over 120, and so on. This is exactly how calculators and computers evaluate sines, cosines, logarithms, and exponentials to this day. Your pocket calculator does not contain a tiny protractor or a miniature circle. It computes a handful of terms of the Taylor series, perhaps 5 or 6 terms, and the result is accurate to more decimal places than the display can show. Every time you press the sin button, a Taylor series runs behind the scenes. Every time a video game engine computes a rotation, a Taylor series is at work. The idea that any smooth function can be captured by an infinite polynomial, that curves can be tamed by algebra, is one of the great unifying insights of mathematics. Euler himself went blind in his right eye around 1738 and lost sight in his left eye around 1766, becoming completely blind at the age of 59. He continued to work. If anything, his productivity increased after he went blind, aided by an extraordinary memory and by assistants who recorded his dictation. Roughly half of his 800 papers were produced after he could no longer see.
He once reportedly said that losing his sight freed him from distractions and allowed him to concentrate more deeply on mathematics. Euler's influence on mathematics is hard to overstate. He did not just solve problems, he created entire fields. He laid the foundations of graph theory with his analysis of the Königsberg Bridge problem. He made fundamental contributions to number theory, proving results about prime numbers that are still central today.
He developed the calculus of variations alongside the Bernoullis. He wrote textbooks that defined how calculus would be taught for generations. If Newton and Leibniz built the engine, Euler was the one who drove it across every landscape in sight, showing what it could do, mapping its range, and leaving roads for everyone who came after. But in all this beauty and productivity, something troubling was hidden, a flaw at the very heart of the enterprise. All of calculus, as Newton and Leibniz had constructed it, rested on the notion of infinitesimally small quantities. A derivative was defined as a ratio of infinitely small changes, dy over dx, where dx and dy are infinitely small but not zero. An integral was defined as a sum of infinitely many infinitely small areas. You used these infinitesimal quantities as if they were non-zero. You divided by them, manipulated them algebraically, and then, when convenient, you treated them as zero to simplify the result. Nobody could explain clearly what these quantities actually were. Were they zero? Then dividing by them is illegal. Were they positive? Then setting them to zero afterward is dishonest. In 1734, an Irish bishop named George Berkeley wrote a short, sharp pamphlet called The Analyst that struck directly at this weakness. Berkeley was no enemy of science. He was genuinely curious about how reliable calculus could be if its foundations were logically inconsistent. His argument was devastating in its simplicity. When you compute a derivative, you divide by the increment h. If h is 0, you divide it by 0, which is forbidden. If h is not 0, you have no right to set it to 0 afterward. Berkeley called infinitesimals the ghosts of departed quantities. And he was right. The buildings stood, the bridges held, the planetary orbits matched the calculations. But the reasoning underneath was riddled with logical holes. It was as if an entire city were rising higher and higher while cracks spread through its foundation. Mathematicians of the 18th century largely shrugged off Berkeley's critique. The method worked, the answers were correct. Why worry about philosophical niceties? But the cracks would widen. New discoveries would produce paradoxes that could not be ignored. And it would take more than a century, an entire generation of rigorous thinkers, to rebuild the foundation without the ghosts. For over a century after Berkeley's pamphlet, the logical foundations of calculus remained unrepaired. Mathematicians used infinitesimals freely, produced correct results, and mostly avoided examining the shaky reasoning too closely. It was as if everyone had agreed not to look down while crossing a bridge they knew was cracked. And for a while, it worked. But the 19th century brought new discoveries that made the cracks impossible to ignore. The trouble began, paradoxically, with one of the most beautiful and useful results in all of applied mathematics. In the early 1800s, Jean-Baptiste Joseph Fourier, a French mathematician and physicist who had accompanied Napoleon to Egypt as a scientific advisor and later served as prefect of the department of Isère in southeastern France, was studying how heat spreads through a solid object. Fourier's life was as dramatic as his mathematics. He nearly died on the guillotine during the Revolution, survived Napoleon's Egyptian campaign in blistering desert heat, and became obsessed with warmth in a literal sense. He kept his rooms uncomfortably hot and bundled himself in heavy coats even in summer, convinced that heat was essential to health. Picture the problem that consumed him. A long, thin metal rod, heated at one end and left to cool. How does the temperature at each point along the rod change over time? Fourier needed to solve the heat equation, a differential equation describing the flow of thermal energy, and in doing so, he made a stunning claim. Any periodic function, no matter how jagged or irregular, can be decomposed into a sum of smooth sine and cosine waves of different frequencies. A square wave, with its sharp corners, a sawtooth wave with its abrupt jumps, even a function that looks nothing like a wave. All of them, Fourier argued, can be built by adding up sines and cosines with the right amplitudes and frequencies. This idea, Fourier analysis, turned out to be one of the most practically powerful tools in the history of science. 2 centuries later, it is everywhere. MRI machines use Fourier transforms to reconstruct images of the inside of your body. JPEG image compression uses a variant to identify and discard visual details too fine for the human eye to notice. Digital audio, every song you stream, every podcast you listen to, relies on Fourier's insight to convert sound waves into numbers and back again. But in Fourier's own time, his claim raised sharp mathematical questions. Some of his series clearly converged to the functions they were supposed to represent. Others behaved strangely. Under what conditions does a Fourier series actually converge? What does convergence even mean, precisely? The existing tools could not answer these questions, because the existing tools were built on infinitesimals, and infinitesimals were ghosts. The person who began the repair was Augustin-Louis Cauchy, a French mathematician working in the early to mid-19th century. Cauchy was enormously productive. He published nearly 800 papers, second only to Euler, and he was also deeply religious and deeply difficult to work with. Colleagues found him self-righteous and politically reactionary. But his mathematical contributions were transformative. Cauchy took the concept of the limit, which had been used informally since Archimedes, and placed it at the center of calculus. He replaced the vague notion of an infinitesimal with a precise statement. When we say the limit of some expression as h approaches 0 is L, we mean that the expression can be made as close to L as we wish by making h sufficiently small. Not infinitely small, just small enough.
The shift was subtle, but profound. Instead of claiming that some mysterious quantity has shrunk to infinite smallness, an object, Cauchy described a process. For any degree of closeness you demand, I can find a value of h that achieves it. The infinite is replaced by as close as you like. The ghost is replaced by a guarantee. But Cauchy's formulations, while much clearer than what came before, still left room for ambiguity. The person who closed the remaining gaps was Carl Weierstrass, a German mathematician with one of the most unusual career paths in the history of the subject. Weierstrass spent his 20s and 30s as a schoolteacher in small Prussian towns, teaching mathematics and gymnastics to teenagers, doing research in his spare time, publishing almost nothing. Only in his 40s, after a single paper on a topic in complex analysis brought him sudden fame, did he receive a university position. He then spent the rest of his career at the University of Berlin, where his lectures became legendary for their rigor. Weierstrass gave the famous epsilon-delta definition of the limit, the definition used in every rigorous calculus course today. We say that the limit of f of x as x approaches a is L, if, for every epsilon greater than 0, no matter how tiny, there exists a delta greater than 0, such that whenever x is within delta of a, but not equal to a, f of x is within epsilon of L. No infinitesimals, no ghosts, only ordinary finite numbers and inequalities. The definition is a logical machine. You name your tolerance, epsilon, and I produce a neighborhood, delta, that guarantees the function stays within your tolerance. It is airtight. Weierstrass also exhibited a function that shattered long-standing assumptions. He constructed a function that is continuous everywhere. You can draw its graph without lifting your pencil, but differentiable nowhere. At no point does the curve have a well-defined tangent line. At every point, it is jagged, spiky, endlessly wrinkled, no matter how closely you zoom in. Before Weierstrass, mathematicians had assumed that continuity and differentiability were essentially the same thing, that any continuous curve must be smooth almost everywhere. Weierstrass showed they are genuinely different properties. A function can be perfectly continuous and yet have no derivative at any point whatsoever. For 19th century mathematicians, this was profoundly unsettling, like discovering that a surface that looks smooth to the eye is actually fractured everywhere when viewed under a microscope. Bernhard Riemann, another German mathematician of the mid-19th century, contributed the rigorous definition of the integral that bears his name.
He spelled out precisely what it means to compute the area under a curve. Partition the interval into subintervals, choose a sample point in each, form the sum of the rectangle areas, and take the limit as the partition becomes infinitely fine. Crucially, Riemann specified the conditions under which this limit exists, the conditions under which the integral is defined. Not every function can be integrated in Riemann's sense. Some are too wild. But the definition drew a clear boundary. These functions are integrable, those are not, and here is the proof. And then came Georg Cantor, whose work on infinity would shake mathematics to its core. Cantor, working in the 1870s and 1880s, asked a question that sounds almost childlike. Are all infinities the same size? There are infinitely many natural numbers, 1, 2, 3, 4, and so on. There are infinitely many real numbers, all the points on a line. Are these two infinities equal? Cantor showed they are not.
His proof, the famous diagonal argument, is a masterpiece of logical reasoning. Suppose, for the sake of contradiction, that you could list all the real numbers between 0 and 1 in a sequence. A first real number, a second, a third, and so on, covering every single one. Cantor showed how to construct a new real number that differs from the first number in its first decimal digit, from the second number in its second digit, from the third in its third, and so on down the diagonal. This new number is a perfectly valid real number between 0 and 1. It is an infinite decimal, like any other. But it cannot appear anywhere in your supposedly complete list, because it was constructed to differ from every single entry in at least one decimal place. The first entry disagrees in its first digit. The second entry disagrees in its second digit. The millionth entry disagrees in its millionth digit. No matter how far down the list you go, this number is not there. Contradiction. The list was supposed to be complete, and yet we have produced a real number it missed. Therefore, no such complete list can exist. The real numbers cannot be arranged in a sequence. They are uncountably infinite, a strictly larger infinity than the natural numbers. The reaction was fierce. Leopold Kronecker, one of the most powerful mathematicians of the era, called Cantor a corrupter of youth and worked actively to block his career. Henri Poincaré called Cantor's set theory a disease from which mathematics will eventually recover. Cantor suffered severe bouts of depression throughout his life and spent his final years in a psychiatric clinic in Halle, Germany, where he died in January of 1918. But Cantor was right, and his ideas won. His set theory became the standard foundation for all of modern mathematics, the bedrock on which everything else is built. Different sizes of infinity, the precise definition of the real number line, the rigorous treatment of limits and continuity, all rest on Cantor's framework. By the turn of the 20th century, the crisis was resolved. Limits defined rigorously through epsilon and delta. Derivatives and integrals defined as limits. The fundamental theorem proved with full rigor. Series tested for convergence with precise criteria.
The building of calculus, which had been erected quickly and brilliantly by Newton and Leibniz and expanded enormously by Euler and his contemporaries, was finally rebuilt from basement to roof with solid, logical masonry. The ghosts had been exorcised, and with the foundations secure, the machine could be pushed to its full power. Let us take a brief tour through the toolkit, the practical methods that make calculus useful for working scientists and engineers. We have seen the big ideas: limits, derivatives, integrals, the fundamental theorem. Now let us see how those ideas are wielded in practice, because the elegance of calculus lies not just in its concepts, but in its techniques. Optimization, finding the best possible value, is one of the oldest and most common applications of calculus, and the procedure is elegant in its simplicity. Suppose you are designing a cylindrical can to hold a fixed volume of liquid, say 12 fluid ounces of soda, and you want to minimize the amount of aluminum used. The amount of aluminum is the total surface area of the can, the top, the bottom, and the curved side. That surface area depends on the can's radius and height, and the fixed volume constraint links the two. If you make the can wider, it must be shorter to hold the same volume, and vice versa.
Calculus turns this practical engineering problem into a clean mathematical procedure. Express the surface area as a function of one variable using the volume constraint to eliminate the other. Take the derivative and set it to 0. At a maximum or minimum, the derivative is 0. The function has leveled off. Its tangent line is horizontal. The slope is 0. Solving the equation tells you the exact radius that minimizes the metal. The second derivative confirms whether you have found a minimum or a maximum. If the second derivative is negative at that point, the function is curving downward like a hilltop, and you are at a maximum. If the second derivative is positive, the function is curving upward like the bottom of a valley, and you are at a minimum. This simple algorithm, first derivative to find candidates, second derivative to classify them, governs the design of bridges, the shapes of airplane fuselages, the pricing strategies of corporations, and the training of machine learning models. Anywhere someone is asking, "What is the best I can do?" calculus provides the method. Integration techniques go beyond looking up antiderivatives in a table. Two methods deserve mention because they are the workhorses of applied mathematics. The first is substitution, sometimes called the reverse chain rule. If the function you are trying to integrate has a nested structure, a function inside a function, you can simplify it by introducing a new variable. You let u equal the inner function, compute du, and rewrite the entire integral in terms of u. Often the result is something simple enough to integrate directly. Then you switch back to the original variable. The procedure mirrors the chain rule for derivatives, but run in reverse. Where the chain rule breaks a derivative apart through nested layers, substitution reassembles an integral by collapsing those layers back together. Think of it as changing the lens through which you view the problem. A function that looks complicated in x may look simple in u, and the integral of the simple form is one you recognize. For example, if you need to integrate 2x times e to the x squared, you notice that 2x is the derivative of x squared. Let u equal x squared. Then du equals 2x dx, and the integral becomes simply e to the u du, which is e to the u, which is e to the x squared. A problem that looked intimidating becomes trivial with the right substitution. The second is integration by parts, the reverse product rule. If you need to integrate a product of two functions and cannot do so directly, you can transfer the derivative from one factor to the other, often producing something more manageable. The formula comes directly from the product rule for derivatives, rearranged to isolate the integral. In practice, you choose one part to differentiate and the other to integrate, and if you choose wisely, the new integral is simpler than the original. These techniques,
substitution and integration by parts, together with a handful of others, cover the vast majority of integrals that arise in applications. They require practice to master, but the underlying ideas are simple. Every integration technique is some differentiation rule run backward. And now we arrive at the place where calculus truly comes alive, where it goes from being a tool for computing slopes and areas to being the language of the physical universe. Differential equations.
A differential equation is an equation whose unknown is not a number, but a function. And the equation involves the function's derivatives. Instead of asking, what number x satisfies this equation, you are asking, what function y of t satisfies this relationship between y and its rate of change. The simplest and most important differential equation is dy over dt equals ky. The rate of change of y is proportional to y itself. If k is positive, the function grows faster the larger it gets. If k is negative, it shrinks faster the larger it is. The solution is y equals y0 times e to the kt, where y0 is the initial value. This single equation, the exponential growth and decay equation, describes an astonishing range of phenomena. Bacterial populations doubling every few hours, radioactive isotopes decaying with a specific half-life, money earning compound interest in a bank account, a drug being cleared from the bloodstream at a rate proportional to the amount remaining. Newton's law of cooling, which says a hot cup of coffee loses heat at a rate proportional to the temperature difference between the coffee and the room. All the same equation, all the same exponential solution. The universality is almost eerie. More complex differential equations describe richer behavior. Second-order equations, involving the second derivative, describe oscillations. A pendulum swinging, a spring bouncing, a guitar string vibrating, an electrical circuit resonating, all obey equations of the form second derivative of y equals negative k times y. The second derivative, the acceleration, the rate of change of the rate of change, pulls y back towards zero, and the harder you pull it away, the harder it gets pulled back. The solutions to this equation are sine and cosine, waves. Sine and cosine are the functions whose second derivative is the negative of the original, which is exactly the mathematical signature of something that swings back and forth around a resting point. This is why waves are everywhere in physics. Whenever a restoring force pulls a system back toward equilibrium, the resulting motion is sinusoidal. Sound waves, light waves, ocean waves, the alternating current in your wall outlet, all are manifestations of second-order differential equations whose solutions are sines and cosines. Newton's second law, F equals ma, is itself a differential equation. The force on an object equals the mass times the second derivative of its position. Given a force law, gravity, electromagnetism, friction, you solve the resulting differential equation to find the object's trajectory. Newton used exactly this procedure to derive the orbits of planets from his inverse square law of gravitation. James Clerk Maxwell, in the 1860s, wrote down 4 differential equations that describe all of electricity and magnetism. Just 4 equations. 4 compact statements about how electric and magnetic fields change in space and time. From these 4 equations, Maxwell derived a prediction that no experiment had yet confirmed: that oscillating electric and magnetic fields should propagate through space as waves, and that these waves should travel at a speed that, when he computed it from known electrical and magnetic constants, turned out to be exactly the speed of light. The conclusion was inescapable. Light itself is an electromagnetic wave. With 4 equations and calculus, Maxwell unified optics, the study of light, with electromagnetism, the study of charges and magnets, into a single theory. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all the same phenomenon, differing only in frequency.
all predicted by Maxwell's differential equations, all confirmed by experiment, all consequences of calculus applied to the physical world. Erwin Schrödinger, in the 1920s, wrote the equation that governs quantum mechanics, the Schrödinger equation, another differential equation whose solutions give the probability of finding a particle in a particular state at a particular time. Every transistor in every computer chip is designed using solutions to the Schrödinger equation. The entire semiconductor industry, and therefore the entire digital world, rests on quantum mechanics, which rests on differential equations, which rest on calculus. The Navier-Stokes equations describe the flow of fluids: water through pipes, air over wings, blood through arteries, weather systems swirling across continents. They are among the most difficult differential equations ever studied. In simple cases, exact solutions exist and are beautiful. In complex cases, turbulent flow, chaotic weather, ocean currents, the equations resist exact solution and must be solved numerically on powerful computers. Proving whether smooth solutions to the Navier-Stokes equations always exist, or whether they can develop singularities, points where the mathematics breaks down, is one of the 7 unsolved Millennium Prize problems, carrying a reward of $1 million. As of tonight, no one has claimed it. Virtually all of fundamental science is written in the language of differential equations. The equations that describe how a star burns, how a disease spreads through a population, how a bridge flexes in the wind, how a galaxy forms over billions of years. All are differential equations. Newton's laws, Maxwell's equations, Einstein's field equations, the Schrödinger equation, the equations of thermodynamics and fluid dynamics. The deepest truths science has discovered about the workings of the universe are all expressed as relationships between functions and their derivatives. Calculus provides the grammar. Differential equations are the literature, the stories science tells about how the world behaves. And those stories, once written, have a power that their authors could not have imagined. Let us surface from the mathematics and look at what it has built. The applications of calculus are so woven into modern life that listing them feels almost absurd, like listing the applications of electricity or of language. But a few examples will show the range. Magnetic resonance imaging, MRI, works by placing the human body inside a powerful magnetic field. Hydrogen atoms in the body's water molecules align with the field. A radio pulse knocks them out of alignment, and as they swing back, they emit faint signals. Different tissues, bone, muscle, tumor, fluid, swing back at slightly different rates, producing slightly different signals. The machine records these signals and reconstructs a three-dimensional image of the body's interior using the Fourier transform. Every MRI image you have ever seen is the output of a mathematical operation that Joseph Fourier developed in the early 1800s while studying how heat flows through metal. He was thinking about rods and ovens. 2 centuries later, his method reveals tumors hidden deep inside the brain. GPS, the Global Positioning System, relies on a constellation of about 30 satellites orbiting roughly 12,500 miles above the Earth, each carrying an atomic clock accurate to billionths of a second. Your phone picks up time signals from at least 4 of these satellites simultaneously and computes its distance from each one based on the tiny differences in arrival time. Since the signals travel at the speed of light, a difference of a billionth of a second corresponds to about 1 foot of distance. But without corrections from Einstein's theory of general relativity, which describes how gravity warps space and time, and which is written entirely in the language of calculus, specifically differential geometry and tensor calculus, GPS would drift by miles within hours. The clocks on the satellites tick slightly faster than clocks on the ground because they are farther from Earth's gravitational pull. Without the relativistic correction, computed through calculus, GPS would be useless. With it, your phone knows where you are to within a few feet. JPEG image compression uses the discrete cosine transform, a close relative of the Fourier series, to analyze an image block by block, breaking each small square of pixels into a sum of spatial frequencies, from broad gradients to fine details. High-frequency components, rapid pixel-to-pixel changes, fine textures, subtle edges, are often invisible or barely noticeable to the human eye. The algorithm identifies those components and reduces their precision or discards them entirely, shrinking the file by a factor of 10 or more with almost no perceptible loss of quality. You could stare at the compressed image and the original side by side and struggle to tell the difference, because the algorithm is exploiting the specific limitations of human visual perception, removing precisely the information your eyes and brain would have ignored anyway. Streaming video, digital music, telecommunications, the entire infrastructure of digital media depends on these Fourier-descended methods. Every time you watch a video on your phone, every time you make a video call, Fourier analysis is compressing and decompressing the signal in real time. Aerodynamics is applied calculus. The shape of every modern airplane wing, every car body designed in a wind tunnel, every turbine blade in a jet engine is optimized using computational fluid dynamics, a technique that divides the space around the object into millions of tiny cells and solves the Navier-Stokes equations, the differential equations of fluid flow in each cell, stepping forward through time. The result is a detailed picture of how air or water flows around the surface, where pressure builds, where drag arises, and how to reshape the design to reduce it. Without calculus, modern flight would be a matter of guesswork and dangerous trial and error, the way it was for the Wright brothers, who tested wing shapes by hand in a homemade wind tunnel. With calculus and modern computing, engineers can simulate thousands of wing shapes in software, measuring lift, drag, and turbulence with extraordinary accuracy before bending a single piece of metal. The same methods design Formula One cars, optimize the shape of high-speed trains, and even predict weather patterns, because weather, at its core, is fluid dynamics on a planetary scale, governed by the same Navier-Stokes equations. Financial markets use stochastic calculus, calculus extended to handle randomness, to price options and manage risk. The Black-Scholes equation, published in 1973 by Fisher-Black, Myron Scholes, and Robert Merton, gives a formula for the fair price of an options contract. The equation is a partial differential equation, closely related in its mathematical structure to the heat equation that Fourier studied. The connection is deeper than coincidence. The diffusion of heat through a material and the random fluctuation of stock prices through time both involve quantities spreading outward from a starting point, governed by similar underlying laws. Scholes and Merton won the Nobel Prize in economics for this work. Black had died by then and was not eligible. Finance, for better and worse, runs on calculus. The 2008 financial crisis, among its many causes, involved the misapplication of these same models. A reminder that a tool is only as good as the judgment of the person using it. Quantum mechanics runs entirely on differential equations.
The behavior of every atom, every electron, every photon is governed by the Schrödinger equation, whose solutions, called wave functions, describe the probabilities of finding a particle in a given state. The entire semiconductor industry, every computer chip, every transistor, every LED is designed using quantum mechanical calculations, which are calculus calculations. The device you are listening to right now, whether it is a phone or a laptop or a tablet, contains billions of transistors whose behavior was predicted before a single one was manufactured by solving differential equations rooted in the same calculus that Newton and Leibniz developed 3.5 centuries ago. And then there is artificial intelligence. In 1986, 3 researchers, David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper describing backpropagation, the algorithm for training neural networks.
The idea had been explored by others before them, but this paper made it practical and launched the modern era of deep learning. At its mathematical core, backpropagation is the chain rule of differentiation. Here is how it works. A neural network is a chain of nested functions. Input data enters the first layer, is transformed by that layer's mathematical operation, and the result is passed to the second layer, which transforms it again and passes it to the third, and so on through dozens or hundreds of layers until an output emerges at the end. Each layer's operation is defined by numerical parameters called weights, millions or billions of them. At first, the weights are random and the output is nonsense. Training means adjusting all those weights so that the output matches the desired answer. The question is, which direction should each weight be nudged, and by how much? The answer comes from computing the derivative of the error, the difference between the network's output and the correct answer with respect to each weight. If increasing a particular weight makes the error larger, you decrease it. If increasing it makes the error smaller, you increase it. The derivative tells you both the direction and the magnitude of the adjustment. But the network is a chain of nested functions, and the error depends on each weight only indirectly, through all the layers between that weight and the output. So you need the chain rule. dy over dx equals dy over du times du over dx. Threading the derivative backward through the entire chain, layer by layer, from the output all the way back to the first layer. This backward pass through the chain rule is backpropagation. Each step adjusts every weight by a tiny amount in the direction that reduces the error. Then you run a new input through the network, compute the error again, backpropagate again, adjust again. Billions of times. Each adjustment is small, a tiny nudge, a tiny improvement, a fractional reduction in the error. No single step does much. But repeated millions and billions of times, across vast data sets, the network converges to something remarkable. It learns to recognize faces in photographs. It learns to translate between languages it has never been explicitly taught. It learns to generate images from text descriptions, to compose music, to hold conversations, to write code, to diagnose diseases from medical scans. Every language model, every image generator, every voice assistant you have ever used is the product of this process. And the mathematical core of that process, the engine that drives every adjustment, is the chain rule that Leibniz wrote down in 1675, applied through the same method of infinite approximation that Archimedes used 2,300 years ago. A tiny improvement, repeated until it converges. The chain rule of the 17th century, inside every neural network on the planet. Fourier's heat equation, inside every MRI machine. Newton's second law, inside every rocket trajectory. The same mathematics, echoing forward through the centuries, into machines and technologies its inventors could not have dreamed of, solving problems they could not have imagined, shaping a world they would not recognize. And with that, our journey through the applications is complete. We have seen calculus at work in medicine, in navigation, in communication, in finance, in the fundamental laws of nature, and in artificial intelligence. We have climbed all the way from ancient clay tablets to modern neural networks. There is only one thing left to do: come home. We have crossed 4,000 years tonight. Egyptian papyrus, Babylonian clay, Archimedes' triangles inscribed inside a parabola, Liu Hui's polygons closing in on pi, Madhava's infinite series in the tropical warmth of Kerala, Descartes drawing his coordinate axes, Fermat quietly differentiating, Newton in plague quarantine, a candle burning low, scribbling the method of fluxions in a notebook no one would read for decades. Leibniz in Hanover, designing notation so elegant that 3.5 centuries of mathematicians would never improve on it. The Bernoulli brothers quarreling over cycloids. Euler, blind and unstoppable, dictating 800 papers from memory. Berkeley's ghosts, Cauchy's limits. Weierstrass and his everywhere jagged curve. Riemann's rectangles, Cantor's different infinities, and the loneliness that followed. Fourier's waves, decomposing everything, heat, sound, light, images, into sines and cosines. And finally, back propagation, the chain rule threaded through billions of weights, teaching machines to see and speak. All of it pulling the same thread, all of it reaching for the same idea.
One idea. If the world is continuously changing, you can understand that change by breaking it into infinitely many, infinitely small pieces and putting them back together. Limit, derivative, integral. 3 concepts, and from them, all of physics, all of engineering, all of modern technology. 3 concepts that took humanity 4,000 years to formulate clearly, and that, once formulated, turned out to be deep enough for everything. And now you are lying here, and the night is quiet. The room is still. But calculus is at work inside you even now. The temperature of the air around you is shifting slightly as the night cools, and that shift is described by a derivative, a rate of change. The blanket over you is transferring heat to your body according to Fourier's law, the same law Fourier derived from his heat equation, the same differential equation that launched an entire branch of mathematics. Your heartbeat, steady and slow, produces an electrical signal that decomposes into a Fourier series, a sum of sine waves at different frequencies, the same decomposition that powers every MRI scan. Each nerve impulse traveling along your arm or leg solves a differential equation, the Hodgkin-Huxley equations, which describe how electrical voltage propagates along a nerve fiber through the opening and closing of ion channels. Even the process of falling asleep, the gradual dimming of conscious activity, the slow wave oscillations that replace waking thought, is continuous change, smooth transition, a function approaching a value. You do not need to understand any of this for it to work. Your body does not consult a textbook. The mathematics is woven into the physics, and the physics is woven into you. The warmth spreading through the blanket, the slow deceleration of your thoughts, the gentle heaviness in your limbs. All of it is continuous change. All of it is described by the same tools that Archimedes began to develop 23 centuries ago. There is something calming in the thought that the world, for all its apparent complexity, is described by such simple ideas. A limit, a derivative, an integral. The questions are the oldest questions humans have ever asked about the universe. How fast is this changing? How much has accumulated? And the answers, once found, turned out to be connected. Inverse operations, 2 sides of the same coin, as the fundamental theorem reveals. That connection is the deepest result in 4,000 years of mathematical thinking. And it is still here, still working, still holding the world together. In the GPS satellites overhead, in the electrons flowing through wires, in the algorithms running in distant data centers, in the slow rhythm of your breathing. 4,000 years, dozens of civilizations, hundreds of minds separated by oceans and centuries, arriving at the same truths. As if the mathematics were already there, woven into the fabric of things, waiting for someone to notice. Let the thoughts go now. They will settle overnight, like the terms of a convergent series, each a little smaller than the last, adding less and less, but together approaching an exact answer. 1 + 1/2 + 1/4 + 1/8. Each thought a little quieter, each breath
a little slower. You do not need to reach the sum. The series converges on its own. You just let the terms come, each smaller than the last, each carrying a little less weight, until the difference between where you are and where you are going is too small to notice. Approaching infinitely without quite touching. Getting an exact answer from infinitely many inexact steps. Catching the instant without stopping time. Counting the whole by summing the infinitely small. The room is warm. The night is long. The equations have all been written, and they will go on working while you rest, in the satellites overhead, in the wires in the walls, in the slow chemical reactions that keep your body alive, in the quiet firing of neurons settling into the rhythms of sleep. You do not need to tend them. They will run on their own, the way they always have, the way they always will. That is the whole magic. And it works. It worked 4,000 years ago, when a Babylonian astronomer drew trapezoids under Jupiter's speed graph, trying to predict where a wandering light in the sky would go. It worked 2,300 years ago, when Archimedes inscribed triangles in a parabola on the island of Sicily. It worked 350 years ago, when Newton wrote his method of fluxions by candlelight in a farmhouse during a plague. It works tonight, as a neural network in a data center adjusts billions of weights, each adjustment a tiny application of the chain rule. It will work 1,000 years from now, in applications we cannot begin to imagine, just as Leibniz could not imagine a neural network, and Archimedes could not imagine GPS, and the Egyptian scribe who computed the volume of a frustum could not imagine any of the extraordinary things his formula would one day be part of. You have passed through all the layers tonight, from the surface down to the very bottom, to the oldest mathematical artifacts on Earth, and back again. From the clay tablets of Mesopotamia to the silicon of data centers. From a scribe writing on papyrus by lamplight to a neural network adjusting its weights in a humming server room. From Archimedes hand-drawing circles in the sand to algorithms processing millions of images per second. 4,000 years of human thought compressed into one night. And through all of it, one thread, the idea that you can understand the changing world by breaking change into pieces small enough to hold, and then reassembling them. Infinitely many pieces, infinitely small, adding up to something whole and exact and true. The journey is complete. Close your eyes, breathe steadily. Let the series converge. Let the terms grow smaller. Let the limit do its work. The story is finished. The mathematics will keep going. It always does. In every satellite, every circuit, every heartbeat. But you do not need to follow it anymore. Let it run on its own, the way it has for 4,000 years. Quietly, steadily, without you needing to watch.